So just a second. So just a second. Yeah, you can start.
Yeah. Hello, everyone. My name is Shuai Chen. I'm from the bigger group in the Erasmus MC, the Netherlands. So actually, I work in the same group with Florian before, and this is the work I'm going to present that I published in 2 years ago on Mikai. It's about multitask attention-based semi-supervised learning in medical image segmentation. So the first is the motivation. There are two motivations. The first is because the annotations in medical images are very expensive and scarce, and to produce it is also time consuming. But we get lots of unlabeled medical images every day, so it's interesting to investigate how to make use of them. The second is some related work. So the first one is more well known. It's the ladder networks published on NeurIPS. In this one, they show that auxiliary autoencoder can improve the segmentation performance, the classification performance from the reconstruction task. So they show that, but it's not for segmentation. So we can't directly use that in the segmentation problem. And the second one is published also from Mikai years ago. It's using the reconstruction features to help segmentation. So here's the question: that can we encourage the autoencoder to learn features more relevant for the segmentation? Because in the second work, they are using the reconstruction features directly, and we don't know how the features from reconstruction are related to segmentation features. And that's the question we want to investigate. So the idea is quite simple. So we want to use the autoencoder to learn both the segmentation and reconstruction features to help the main task, which is the segmentation. So the framework is, sorry, I can. Yeah, the framework is consists of two parts. The first part is the normal unit with skip connections, and from the encoder path to the decoder path. The second part is the autoencoder part. That the autoencoder share the same encoder part with the unit, but with its own decoder. Usually before that, people use similar architectures in the multitask learning. So they use one path to learn the segmentation and another path to learn the reconstruction task. So here is a problem that if we directly do that, the two tasks are not connected. So they are. That means, for example, the reconstruction task try to compress the images into a high-level space, and that may conflict. Some features may conflict with the segmentation features, and if the reconstruction task features are very large, that they may conflict with the segmentation features in the same encoder and decrease the performance. And this is also what we observed in the experiments. So if we want to better fuse the two features, we hope that the features learned are not separated for each of the two tasks. We want the features can contain the information for both tasks. So this is what we changed in this architecture, that we use attention mechanism here. This is a simple one. We just use the element-wise product from the input features to the soft segmentations here from the unit to generate new images, which is the background and the foreground. So the background and foreground actually contains the segmentation information. So they indicate the voxels belong to background or foreground. And this is also the images that we want to construct using the second autoencoder. So that means the autoencoder is actually doing segmentation and reconstruction at the same time. And we hope that in this way, the autoencoder can learn segmentation features and reconstruction features at the same time. So it may be not very straightforward, but we should know that before that, it's not possible to use autoencoder, and it's not possible to use UNet to do the two tasks at the same time, because if we want to use the UNet to do the reconstruction, it will copy the feature from the first layer to the last layer directly without learning anything. So that's the problem. If we want the same encoder to learn both features, we have to use it in this way. And there are also two ways to optimize it. The most common way is joint learning. So we train the two tasks at the same time. And the second way is the alternative training. So we can use, we train two tasks alternatively with two different optimizers. So this is inspired by the observation that we think these two tasks have two different optimal step size during training. So maybe it's better to use two different optimizers for each of the two tasks, but not the one for both. And we can see some results.
Questions from the last slide?
Yes.
Yeah, so for example, yeah, like the reconstruction, like background, foreground, like yeah, I mean, so these are the ground truth, right? But the reconstruction, like below, at the output of the decoder, it's not perfect, right?
It's not perfect. Yeah, that's true.
Like, how good does it need to be to help? You know, like, is this enough, or even if it were worse, like, would it be still enough? And maybe like behind that, the questions like, how do you balance the two losses? You know?
Yeah, that's a nice question. So first, I want to answer this one. This is the background, foreground, and they are the ground truths, depend on whether it's labeled or unlabeled images. For example, if we input labeled images, we can just use the ground truths to generate the new images. And if we have the unlabeled images, we can generate the images based on the pseudo labels. That's the soft segmentation from the unlabeled images. And in this case, we can always make sure that the autoencoder has something to learn. It will always get the foreground and background. And for segmentation problem, the most important information is actually the boundary. And in this way, the segmentation, the reconstruction task will focus more on the reconstructing the boundaries, but not to reconstruct the irrelevant thing in the reconstruction task. That's for the first question. For the second question, like how good should the reconstruction be to help the segmentation? That really depends on how much you want to compress the image, because we know that the autoencoder actually compress the image into a high level information and try to reconstruct it. And maybe the high level reconstruction could be more abstract and representative than the high level features learned from the UNet. For example, maybe the UNet, if the segmentation task is quite easy, the UNet will prefer to use like the first two layers to solve the task, but not to use the deeper layers. And in this way, we actually encourage the whole encoder to do the segmentation, but not to use the earlier layers, even it's a simple segmentation task. For example, if the information, if the object we want to segment is quite easy, the UNet, the first layer is already enough. But maybe that's not really about the key clue to segment. So all the deeper layers are wasted. And in this way, we can make full use of the autoencoder. And if we want to make the full use of the autoencoder, the reconstruction may not be perfect, because if it's perfect, then that means it's quite easy to reconstruct. There are not so many information in the image. So that's depends on how we design and how much we want to compress the image.
Okay. And did you experiment with that? Like, do you have like a, you know, like maybe a plot that shows like how it evolves?
For the experiments, I'm using the same autoencoder architecture as the unit. So it's not really enough to reconstruct the whole image, because the whole image is quite complicated. But even it's not perfect reconstruction, it can still aware of the background and foreground in the deeper layer, which I will show in the results part. I will show whether it's aware of how much it will realize the background, foreground.
Okay, thank you.
So this is the quantitative results. We tested on 2 datasets. The first is the breast 18 datasets, and the second is the wet matter hyperintensities. We choose these 2 datasets because these 2 datasets had 2 completely different foreground and background distribution. The first one is the brain tumor segmentation, which has a larger foreground. And the second one is WMH. It has a very small foreground. It's like a few voxels, just a few voxels. So if the number indicates like 20 and 100 indicates we use 20 labeled images and 100 unlabeled images. And the 120 images are the fully supervised setting. We use the same images for both unlabeled and labeled images for both 2 tasks. So we can see that when given very, very few images, in our method, we already achieve competitive results as the fully supervised one. And this is better in the breast datasets, but not in the WMH dataset. That's probably because the foreground difference are really large in this one. So given very few labeled images, all the methods are not performed very well. I'm sorry, maybe I forgot to introduce the different methods. So the blue line is the unit, the baseline. The green one are the pre-trained. That's very traditional. So we just pre-trained autoencoder and using the unit to do the segmentation task directly. And pre-trained deck, that means we only we pre-train only the decoder. And the pre-train unit, that means we pre-train the whole network. We pre-train the encoder and only retrain the decoder later. So this is and we can see that it's not that good. So that means if we just train the reconstruction using the autoencoder, the encoder may not contain that much useful information for the segmentation task. And the MSSL is the traditional multitask learning without the attention thing. That means the reconstruction will just learn reconstruction features, and it's not also not optimal. And the MSSL is the proposed method, and we also fine tune the hyperparameters to balance the 2 tasks. So the 0.7 and 0.9 means the hyperparameter to balance them in the joint training, and the alter means the alternate training. And it showed that alternate training actually worked much better.
Question about alternative training. So do you have like one batch for one loss and the next batch for the same loss, and they have the same number of samples per batch?
Yeah, we use one batch for one task and one batch for another task. So that's alternate. Okay. And you can also consider to alternate between epochs, but we are afraid that if you train one task for a really long time, it will also overfit to one task very quickly. So we use the batchwise alternate training, and this shows that indeed these 2 tasks has different like optimal step size. That's why we need two different optimizers to optimize it. Yeah, so these are the three conclusions we can get from this table. The first is, in both semi-supervised or fully supervised setting, our method is much better than other baselines, and the other baselines are actually the common ways we do it before. The second one is alternative training is better than joint training. No matter how we fine-tune the weighting parameter, it's still better, because even we fine-tune it really carefully, we can still get a trade-off between the two tasks. We can never achieve the optimal step size. And also it shows there is an information gap between the a proposed method and UNet. So that means our method may extract more informative features from the reconstruction, from the new proposed task. That is a combination of the reconstruction and segmentation. So that's, as I mentioned before, I want to show, because people may ask whether the encoder really learns what you said. And in other words, how do we know that the proposed method really learn more discriminative features than other baselines? So we do because the two networks, the UNet and autoencoder, share the same encoder, so we can do analysis on the encoder features. We conduct linear regression on each voxel in the hidden layers. There are 5 layers to investigate how discriminative between the features about foreground and background. So here is the score, and also the 5 layers. They are we do the analysis on the 3 methods. The first one is the UNet baseline, and the second one is the multitask baseline without the proposed method. The third one is a proposed method with alternative training. So we can see that the UNet usually use the second layer to distinguish between the foreground and background, and the traditional methods actually quite average and didn't really use the deeper layer. And in our method, we can see that even with the deepest layer, it's still doing the segmentation. So it can still distinguish between foreground and background. That means we are really making use of the full power of all the layers in the encoder to help segmentation. We can get 3 small conclusions from that. So first is the proposed method is more discriminative in deeper layer. And second is traditional multitask learning is even less discriminative in deeper layer. We can see that is even worse than the UNet. That means if we don't put attention on the reconstruction task, the reconstruction task features cannot represent the features for the segmentation. So it will not distinguish between foreground and background. I can see that will help segmentation. And the last one
question.
Mm-hmm.
Sorry, yeah. So the MSSL what's the difference with your approach, that there is not this attention layer, but they still like separate into foreground, background?
No. The MSSL is just reconstruct the image directly, just reconstruct original image directly. And the MASSL is distinguished with background, foreground.
Okay.
Yeah, because the MSL is usually what people do before in the multitask learning. People train the autoencoder on reconstruction task to provide regularization for the segmentation task. And if the regularization is too much, it may also hinder the performance because the learned features may not relevant for the segmentation.
So it means that with your method to compute background, foreground, you need to have the labels. So unlabeled images, actually MASSL and MSSL are the same, right? It's just on labeled images that's different.
The MSSL can also deal with unlabeled images because it is reconstructing the the original image.
Yeah, but your method there, it cannot separate into background, foreground, right? So
yeah,
it will be the
they
same.
can separate. They can separate background, foreground.
Yeah.
So
okay.
We can see that we also it's also equivalent that we propose a new task. The new task is combination of segmentation and reconstruction. So we can't really say it's reconstruction anymore.
Yeah, okay.
Yeah, and for some conclusion is that autoencoder, we found that in the segmentation problem, the autoencoder may work better as an auxiliary task by doing both segmentation and reconstruction. So if we just do reconstruction, the learned features may not be representative for segmentation problem. And the second one is that the proposed method is promising segmentation framework in both semi-supervised and fully supervised setting. So because in the fully supervised setting, the learned features can also make the deeper layers of the encoder more discriminative than the traditional multitask learning. There are also some messages that's maybe a little subjective. So I think the conflict between segmentation and reconstruction may harm the segmentation performance and make the encoder less discriminative in deeper layers. This is what we observed in this one. And it should be noted that we only do the analysis using the linear regression. So we only show the power of linear regression to separate foreground and background. And that's maybe if we use more advanced regression methods, maybe this may change. So this conclusion is not quite solid. And alternative training may reduce the conflict between different tasks. And this is also what we observed here, because the alternative training is better than just fine-tune the weight between the two tasks. So I recommend to consider the alternative training in the multitask learning in your future work rather than the joint training, and see how it goes. And that's basically the presentation. Thank you. Do you have any questions?
Thank you. I have some questions, but I've asked some already. So if other people have questions, please please ask.
I have a quick question. Hi, that is a great presentation.
Hi.
I was wondering if you tried using the representations that the encoder learns for other tasks like transfer learning, or is it supposed to be used only for this particular setting?
So the basic idea of the attention based, because here we only use a very simple one. We just use the element-wise product. So the general idea here is I want to use the autoencoder to learn to solve a new task that combines the main task and also the auxiliary task. For example, if you are doing detection here, you can also try to combine the detection and the reconstruction in the autoencoder rather than just doing reconstruction. So it's quite general, and we apply this in segmentation here, but it can also be generalized to other problems.
Got it. Okay, thanks.
Yeah, that's a nice question, actually.
Like related to that questions, so like have you tried now you do just like binary segmentation, right? But have you tried with multi-class or different objects like from different classes to segment?
Yeah, that's a good question. So if I'm also curious on the multi-class segmentation because in this work, the breadth datasets and WMG datasets, they actually have more modalities. The WMH has 2 modality and breadth dataset has 4 modalities. So that they can generate like 8 foreground and background and 4 background, foreground for each one. And for the multi-class, they will also generate foreground 1, foreground 2, foreground 3. So they will generate more. That's also make the reconstruction complicated. Here I only use the binary mask. So, but I think if we use it will also work for the multi-class training. But that will require maybe more space for the more capacity for the autoencoder, because we actually increase the number of images to reconstruct for the autoencoder. So we also need to consider that. So given enough capacity, I believe it can apply it in this situation.
Okay. And what if you would have, like for example, now here you're trying to segment a brain lesion. Mm-hmm. What if your like background foreground task it were like something that's not related to the brain to the lesion, but maybe segmenting like an organ in the brain, so not directly related to your.
Yeah, that's really a good question. So this maybe I forgot to say something about that. So one point that's I want to fuse these two tasks is that the reconstruction may focus on some area that we are not interested in. For example, we want to segment the tumor, and maybe in the whole brain, the tumor is not the really complicated area for the brain. It will maybe complicated in other textures. And then the reconstruction task will try to reconstruct that part. And that part is not where we are interested in. So we actually, by using the attention mechanism to force the reconstruction focus on the boundaries of the tumor. So so it will learn. So the features learned will be more relevant for the area we are interested in. This is also one motivation of the work. So indeed, that's this work can move the reconstruction focus more on the area we're interested in.
Okay, thank you.
Mm-hmm.
Thank you very much. So if there are no other questions, then I propose that we stop here.
Yeah.
Yeah. So thank you very much. And
yeah, if you are interested in this work, you can also make comments or send email to me later. Can have more discussion.
Exactly. Yeah, and the link of the paper is in the speaker schedule.
Yeah.
Okay, I'm going to stop the recording. No, I cannot do it. Can you do it, Sarah?
Sure, let me try.